but it's good. I have all the tools in my toolbox, so I can collect the feedback from you guys. I can check how well you are studying, and I like this a lot.
You say stress is good until I can't take it anymore.
I did my sabbatical in Mainz last semester. It's all collaborative teaching. It's all sections. You have to keep the same across all the sections. And I'm not allowed to give quizzes to students. That's crazy. And I'm not allowed to give homework assignments and collect them and give them feedback. So it's all online. It's using that to master engineering something. So you did online. It's just multiple choices. You click, and there were 100 students in my class for circuit 1. 3 sections. Other professors are teaching another 2 sections. So I think only 30 or 40 students are really paying attention, and I'm constantly having only 50 students in the class. So another 50 are just not coming at all for the whole semester, because I'm not allowed to give quizzes, so they don't think it's worth the time to come to class. And I think a lot of them are cheating because it's just multiple choices, right? They stay in the dorm and looking at other people working on it and just copy. So.
Yeah. Are you talking about for circuits using like the non-mastering thing?
You guys?
Yeah, we use that as well, and I thought that was horrible. Because our teacher was like, okay, even if you can guess 20 times, each time you guess, your overall score goes down by like 1 point, and you're like trying to like do this question, and you're at like the 0.1% of the question left, and you're just like, all right,
got you.
0.
But we're able to get some quizzes or feedback from assignments, at least. Yes. Exams?
No, not really.
We didn't get really any feedback.
Yeah, it was like bro was like, okay, here's this, made
Gotcha.
us some math, couldn't follow it, and then
Gotcha,
he was like,
gotcha.
all right,
Okay.
here's the exam on this thing that I never showed you.
Okay. Got you.
Literally
Alright.
threw himself into the deep end instead of trying to swim.
Pretty much, yeah.
Okay. Heard you. Yeah. So that's why I'm telling you, I like all the tools in the toolbox. I can control a lot of things, which is great. All right. So let's get into the topic. I think we were we just finished the superposition, and now we are supposed to work on the DAC. It's called R-2R DAC. You already saw the circuit on Tuesday in the lab. It's a really simple resistor string. So today is just do a circuit analysis about how to calculate the voltages, specifically the output, the VL. The circuit looks like this. I'm drawing a 4-bit DAC. Here's VL. And I'll leave this to you later. The 2R, R, 2R, 2R, 2R. Okay. If you consider this as a chip or digital block, you only worry about the input and output. This is the input, 4 digital inputs and 1 analog output. So before we run any calculations, should I label this as D? So it's 4-bit DAC. So expecting D0 to D3, right? As inputs. So which one should be D3? Which one should be D0? So D3. So we are writing down the 4-bit binary number is actually D3, D2, D1, D0, right? So that's called what? MSB, most significant bit. This is LSB. Okay. So for here, which one has a more weight? or bigger contribution to the VL? You think?
The first one.
The first one should be D3. We'll see why in a bit. Don't worry about that. So D2, D1, D0. So in that case, if I have O1s, this number, 1, 1, 1, 1, the VL will be the maximum number I can give from the input. So the max number I can get from this DAC, okay? So what that max number is, we're going to do the calculation right now to figure that out. So the way to do that is, because these are, when you give a 1 to it, what's really happening is you are connecting a power source, you are turning on that power source. So D digital pin is 1 or 0s. Whenever it's a 1, you are directly connecting a power supply to it, right? So giving a 5 volts. That's assuming it's a 5 volts logic. You are giving a 5 volts to this. If it's a 0, you are shorting this to ground. So that's the difference. So when you do analysis, this could be complicated because you have all the resistors. Sometimes you have a power supply in the middle. So I think usually the best way to do analysis for this type of circuit is superposition. So we are actually doing a superposition to calculate VL for this case. So recall what we did on Monday. For example, we have a D3 only. D3 only. So what's happening is, for here we have equivalent circuit like this. R, 2R, 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 R, R, R. D3 only. And VO1, right? It's VOut1. The first Vout we are getting from this output. So what is Vout1 here in this case? This is the easiest case because all these are grounded. It's just parallel resistors. We did the similar circuit analysis yesterday during the lab. As you can see, you can start combining resistors from the end, left end. But looking into here, if you treat this whole thing as a black box, this is basically 1R, right? It's 2R in parallel. They are shorting this ground pin here. This is basically 2R in parallel. So it's giving you 1R as the equivalent circuit. So that 1R put in series with this R. Okay, it's R and R, so eventually you're getting a 2R here for this whole thing. 2R. Okay? So 2R for the black box. I got a 2R again. So 2R in parallel with 2R is what? 1R again. Okay? So you're getting a 1R for the black box over here. So 1R ground, and you got a 1R added to 1R, you're getting a 2R again. So for this black box, it's going to be 2R. It's okay if you're not following, just watch the video later, okay? So getting 2R from this node. By looking into the black box, it's 2R again. Like a 2R again, you got a 2R. Okay? So getting a 1R again. Okay? And 1R being added in series with this R is 2R. Okay? So it turns out to be a voltage divider circuit. It's 5 volts. This is 2R in ground. So 5 volts out, you got a 2R first. And you got a 2R connect to ground. And here's VO1. It's 5 volts. So VO1 equals what? 5 over 2 volts, 2.5 volts. So the MSB of this DAC is contributing 2.5 volts for VL. Remember, it's a superposition. When we are adding more bits or changing these bits, it's basically adding to that result, adding to that analog voltage. That's the magic of superposition. You might be wondering why you can do that addition, right? I think I searched for that theory, a few years ago, and explanation on Google Wikipedia is really long for this simple theory. I don't think we need to care about that, right? Superposition is the most wonderful circuit theory in this area. You just need to know this works. It's not just applying to DC voltages, but also AC and DC mixed. If you add a DC voltage to AC, you're adding a DC offset to the AC voltage. It's just working. It's working. That's the physics of voltages, I think. It's great. So now we do a second one. Let's start from another page. D2 only. D2 only. VO2. So D2 only means I'm going to short all the other voltage sources. So it's going to be ground, ground, ground. And this is 5 volts. So what is this digital input being put in the nibble? What is it?
Oh, you mean
Yeah,
like
yeah.
0, 1, 0, 0?
Yes, 0, 1, 0, 0, right? Okay. So you still want to find the equivalent circuit here first. And you know that the whole thing here will be what? 2R. So this is actually 2R. So what's next? That's the question. What's next? So from circuit 1, you know that you can, because it's both ground, right? You can put it down and make a short circuit and draw the equivalent circuit and find out using like MASH method or no voltage method to find out the voltage at here. But we don't really do that here over here. Since if you imagine you got a voltage here only, like D1 only, and the circuit over here becomes pretty complicated. You have multiple nodes, multiple networks, or multiple meshes. So we don't do that a lot of times. Okay, so just use superposition. Use superposition. So find out the equivalent circuit first over here. You treat this part as one. Yeah, 7 is. Let's treat this one as a circuit, and you treat this node as one node, and this another node. Okay, and the whole thing here as a load. Can you imagine that circuit? Could be a little bit weird. So if I draw it here, it looks like this. So the voltage source 2R, and directly shorted to 2R to the ground, and got a network, got a terminal here. So that's the terminal, and whatever here is a load. Can we do that?
Yeah.
Yeah. So we can find out the equivalent circuit here, and now we know this is 5 volts, right? It's not changing this voltage value here. So we can treat this with 7 is equivalent, and this one we all know that this is VTH is 2.5 volts, and you're looking backwards, it's actually 1R. So this circuit is equal to this 5/2. 1R, and with a terminal, with the opening. So you are basically connecting this whole circuit. We're connecting this circuit to here. And we don't worry about the load here for now. Okay? And then, since we already have the 7 is equivalent, we can start drawing the load here, put it back here. So it's definitely 1R first, and then a 2R to ground. And here's VL2, let's say VL2. Is that right? Yeah. So what is VO2? It's pretty simple. So 5/2 is being, the 5 halves of that voltage is being divided by 2 again, right? So you're getting 5/4 of volts was the output. Any questions on this? Because this is 2R is 2R. It's being divided one more time. Any question on this? Great. Then if we keep doing this, VO3, D1 only. D1 is over here, and we are adding a voltage source to it, 5 volts, and ground, 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 2R, 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 sorry, 2R, R, R, R. So this is R, and this is adding this to it is 2R. So you can treat this circuit as the original circuit. You can find out the Thevenin's equivalent to it, and the whole entire circuit here as load. So this is the terminal. This terminal. Okay? And what you're getting is Thevenin's equivalent is over the same circuit, because you are always getting 5 volts and being divided by 2. 2R, 2R, and here's a terminal. And then you connect the following circuit to it. So first we convert it to the Thevenin equivalent, which is 5/2 R. Okay, then we add this part to it. So it's R again, and 2R. And R, no, 2R. We can keep applying that Thevenin's equivalent circuit here, because this is definitely a combines this two, right? Combines this, it becomes 5/2, 2R, 2R. Definitely you have all the other methods. It's all grounded. So then apply Thevenin's equivalent circuit one more time. Okay, because you can consider this as a terminal. So this becomes 5/4. R. So this is shorted, they are both ground. So this part, Thevenin's equivalent, becomes this. And then you connect this remaining circuit to it. So this becomes, wait, is that right? I think so. Yeah, yeah, that's right. Yeah, so this is 5/8 volts. Any question on this? No? Okay. I'm not wasting your time. There will be a quiz on Friday about this, okay? Make sure everyone can do it and get a credit. So the last one, D0 only. D0 only. VO4. 2R, 2R, R, 2R. So this is your original circuit. So sum the equivalent, you're getting 5/2 R, and this is a terminal. Here's a terminal. To keep doing the same thing, eventually VO4 you can expect what? 5/16. So my question is, what's the LSB in analog voltage? LSB in analog?
It would be all four of them added together.
No, LSB. So for digital circuits, you have a D3, D2, D1, D0, right? So we know that if, for example, if we are giving a 1101, a digital input like this for the DAC, so we know this is LSB, right? But it's a 1, it's a 1 LSB, it's a digital number. But if I'm asking you a LSB in analog voltage, yeah.
5/16 volts.
Yeah, 5/16. That's the smallest change you can make to the circuit, to the input, or to the output. To the output, actually, yeah, because of the analog voltage. So digital input give you analog output. So the smallest change you can get is when you are flipping this bit, this LSB bit, you are flipping it, 1010, you are flipping it, you are making a 5/16 voltage changes to the output. That's the smallest, it's the resolution of the DAC. Resolution of the DAC. If you're expecting a change lower than 5/20, for example, the whatever company is asking, the contractor is asking, is requesting that, hey, I want a DAC and the voltage output I hope to get when you are feeding any digital input into it, and the smallest voltage change I need from the output will be 5/20. Could a 4-bit DAC do that job for you? No, because smallest you can change is 5/16. So what can you do? Yeah, increase it to 5 bits. So what's the smallest change you can do for 5 bits of DAC? 5/32, right? Okay, cool. Similar to the ADC resolutions, because the DAC is a digital analog converter and ADC is the analog to digital converter. ADC, analog. Converter. We are building most of the parts of the ADC, the real ADC in this class. If not we are hoping we can build the whole thing, but we'll see. I'm super busy this semester, but at least we'll be able to build some of the whole circuit and the registers and the DAC and the comparator. We had an ADC that works to some extent, but not fully functioning. We want to just improve it a little bit, but at least we will be able to understand how the ADC works and how we can build ADC in VLSI, electrical VLSI or cadence. So that's part of the goal of this class. So ADC is a big deal. Doesn't like DACs are usually pretty simple, but ADCs are pretty big circuits. I can say maybe somewhere around 1,000 transistors. It's a lot of circuits, lots of transistors in there.
So I might have missed it, but what did LSB mean?
VLSI?
LSB?
Oh, LSB.
Yeah.
LSB is the least significant bit. So MSB will be the most, right? because if you have a digital number here, 1111, right? You're flipping this bit, which is called the LSB bit. It's just the least significant one because it's changing the whole number the least. That's what's called LSB. And this is the MSB. Okay. So a question from the homework assignments. Since we don't know the structure or the circuits of the ADC for now, but it's just some concept you need to know as the basic calculations. You don't have to know the circuits of the ADC in order to use the ADC, because in Arduinos we do have analog ports. You probably have seen the Arduino chip in M9, right? You have A0 to A5, I think. So these are all analog inputs because behind that pin there's ADC over there in the chip. So it's able to take that analog input and convert to digital input, digital signals, and being put into the CPU and for calculations. So in that case, we need to know how to calculate the resolution of the ADC for certain applications, like the example I gave to you over here. For example, the application requires this resolution, so you calculate back to see how many bits do we need. Then you do a down selection. Okay, because there are all different types of ADCs or DACs on the market. Definitely more bits will give you a higher resolution, but it's also more expensive. So you don't need the overkill. Whenever it satisfies your application, you just pick up the one that just works for the application. You don't need a super high accuracy or precision for the ADC or DAC. So that's why we need to do some of the calculations. So the ADC, usually for the system like Arduinos, it's a 5 volts logic, and we are using that VDD as a reference voltage. But how? We don't need to know that. If it's given like 5 volts as a reference, usually the VDD is the reference. They will allow you to have different choices. You do have a VDD like 5 volts, but they will let you pick up a different reference voltage. But usually 5 volts, we use the 5 volts as a reference. So that reference voltage means the whole range you can convert, you can digitize, will be 5 volts.
Isn't
So
there usually like a 3-port volt as well in there?
3.3 volts?
Or 3.0?
3.0 volts is less common, but usually 3.3 volts.
Okay.
Yeah. So 5 volts, for example, for this case, okay, for the Arduinos, and you have a 10-bit ADC. It's trying to resolve the 5 volts range using this 10-bit ADC. Just basically try to resolve every single step in here until 5 volts. So the smallest step you can increase or decrease from the input, being resolved from the input. A smallest change can be resolved from the input will be 5 volts at the full range divided by all the steps. How many steps can you have for 10 bits?
10,000 or 1,028 or something?
Yeah. So it's a 10-bit resolution of the ADC. Totally you have 2 to the 10th combinations. And why we are doing that, you don't have to know that for now because you don't know the circuit structure for now. So we just need to know if it's a 10-bit ADC, we have 2 to the 10th of combinations of the numbers, so you can resolve 2 to the 10th steps for the 5 volts range. It's something you need to know for now. Okay. So eventually, every single step, the smallest step you can have for this system, becomes 5 volts divided by 2 to the 10th. And that will be the smallest voltage that can be resolved by the ADC. So which means if you have, so what is this voltage for now? Let's just do an estimate. Because the 2 to the 10th is 1024. It's about 1,000. Okay? So you can imagine this will be 4.8 millivolts. Because 5 divided by 1,000 will be 5 millivolts, right? So this we can expect this is like 4.8 or something, 4.9 millivolts. If this system requires, I mean, for analog signal in the environment, you are trying to digitize, trying to detect, okay? And that analog voltage change, for example, from the temperature sensor, okay? That change you need to have, you need to detect is 1 millivolt. Why? Because let's just give you an example. The temperature sensor is giving you 1 millivolts changes, and we need to detect the 1 millivolts change, because whenever it's higher than, when the change is over 1 millivolts, we need to trigger some security operation in the circuit to do something, right? Could be a fire alert, could be something else. And that change from the sensor, from the temperature sensor, is 1 millivolts. So this ADC will fail that application because it's not able to detect the 1 millivolts. The smallest resolution, smallest change it can detect is 4.8 millivolts. So now if you have a 1 bit increase, like 11 bits, so you're having 5 volts divided by 2048. So somewhere around 2.5 millivolts, still not enough, right? You just keep doing that. Probably you are expecting 13-bit ADC. But usually you don't have a 13-bit ADC from the market. You can find 10, 12, 14, or even higher. There are some 20-something bits ADCs, can you imagine? So the application for that is usually very small changes from the analog signal. Do you know what type of analog signal is being detected by that high resolution ADC? Have you used that before? Let's go strain gauges. So strain gauges are detecting pressure or force. That will be used a lot on the market in the future. Think about humanoid robots, and I got to know these kind of things by attending conferences. So that's why I'm thinking it's very important. If you guys stay in the field, you want to attend IEEE conferences. No matter what, robotics, embedded systems, integrated circuit design conference, just go there and talk to the people in the conferences. You'll learn a lot. But most of the time you attend all the lectures, you just don't know what's really going on when they're talking about the research. But you can still learn a lot. So now the challenges for humanoid robots is what? The fingers.
Yeah.
Since we can think about like our fingers, what our fingers can do in the real world. It's amazing. Okay? Still a lot of unsolved challenges. For example, the fingers can feel the texture. If you touch something, it's a very complex process in your brain actually. If you touch, for example, I'm touching the table, I know it's not metal because there's some like heat dissipation. It's not as fast as metal. So if you want the robot to feel the same thing, you need a temperature sensor there as well, and doing some derivative of the temperature changing, a delta T of the temperature to tell it's the metal. So in the future, if you need some robot to do some housework and it's pretty much everything in the house in the future combined with AI, it's going to happen in 10 years, I believe. But just a lot of challenges. We want the humanoid robot to do the same thing as real person assistant can do in the house, right? Housework, healthcare will be very important. So in the past 20 years or something, the robotics became super popular when we developed digital circuits, analog circuit sensors 20 years ago, but started becoming unpopular for 10 years or 15 years. But just in the recent 5 years, it's become super popular again. And it can, people are investing into Tesla, SoftBank, it's an investing company in Japan. They're investing heavily in Boston Dynamics. So all these companies are gaining a lot from the stock market because we know that's a near future. In 10 years, there will be robots doing all the housework at home. And a lot of people will lose their jobs. For example, the doggy hotels, right? I mean, when we are traveling overseas for 10 days or 2 weeks, it's okay, it's gonna be fine. We just leave the dogs at home, in the house. There will be a robot taking care of everything of the tasks. Healthcare, right? Nursing homes. All these people will lose their jobs. Yeah, and we don't have to worry about retiring, at a very old age anymore because someone will take care of us, and all the younger generations, your kids, will never feel like being responsible to take care of you when you are like 80 plus, 5 years old. They will just do their own things. They just travel and do their own things, right? And we just set up in a house with the robots. Yeah. It's a very bright future. Okay. So for this example, 0 to 5 reference voltages. So a robot will be a hardware. So you can imagine in the future we will need a lot of hardware engineers, program hardware embedded systems or IPGAs. We're making chips and work with AI algorithms. It could be AI accelerators, like NVIDIA are making those accelerators, or it could be just very simple circuits. And people are losing their jobs over there, but there will be a lot of a demand on probably from the repairing robots, technicians, salesperson of robots, representatives of the robot companies, right? Anything else I can think of? Parts, supplies, right? Lubricants with joints.
Supervision, I guess?
Supervision of the software, security, yeah. Services. Yeah, exciting. So you guys are 15, 20 years younger than me. You will enjoy this kind of world a lot more than me. You can imagine 10 years from now, we will have robots everywhere. Great. So, come back to this type of problem, okay? It's given that the problem requires a 1 millivolt change. So 0 to 5 volts reference. And it's 1 millivolt change of sensitivity required. What type of ADC do we need? This is another thing you need to know, because whenever you are asking questions from the interview with the company, and when they are asking, like, do you have any data acquisition experience with embedded systems? Okay, they will ask you about, hey, what kind of ADC have you used? Right, they'll ask you. You can say it's okay if you just tell them, I've been using the Arduino's embedded internal ADCs. It's okay. You don't have to use a separate chip. You can purchase chips from microchip. Individual ADCs plug into the socket on the board. It's sometimes it's a higher performance, better performance of these chips, but also for most of the cases during undergraduate studies, with the senior sum projects, I think it's okay just to keep using the Arduino's 10-bit ADC. Okay, so when they ask you about the resolution of the ADC, you want to say how many bits. Okay, keep that in mind. It's a very common question in the interview. So what's the resolution of the ADC have you used? You don't answer anything else. It's going to be just how many bits exactly. Okay, nothing else. Just how many bits. So for this one, I'm asking you the resolution of the ADC to be used. It's actually doing the down selection. So when you know that you need this is reference voltage 0 to 5, so the whole range is 5 volts analog wise, and you know that the sensor or the system requires a 1 millivolts change at the smallest, and you want to be able to resolve it. So now the question is, what kind of resolution of the ADC would you like to pick up? It's a down selection, right? You start searching on DigiKey. Okay, look at the resolutions. That's how that works, right? So what's the resolution? How to calculate it? Really practical problem.
5 over 2 raised to the n, and then find the smallest n that satisfies that condition.
Wait, no, sorry, not this one. So 5 over 1 millivolt change, because these are both analog voltages.
Yeah.
As the entire steps versus what? So that's the resolution you need, right? We don't know that yet. We're just writing down equation to calculate that number.
What else was you?
1. Because 1 millivolts versus 1 LSB. So 1 LSB is basically just 1. Digitally. Okay? 5 volts is the entire range. This is all the steps you need. This is how many steps you need to the x. And that's the range. That's how many steps equals. Oh no, sorry. 5 volts versus 1 LSB equals the entire number of steps versus 1 LSB. And then you can calculate that by doing log base of 2, 5 volts over 1 millivolt. So that's going to be x, right?
Yeah.
And that will be log base of 2, 5,000. If you run the calculation on that, I think that is 12.288. That's weird. We need an integer for the number of bits. 12 or 13? 13, right? 12 is not good enough. You need a 12, more than 12. So the nearest integer of that one will be 13. So there's 13 bits for the ADC. But if there's 13 bits of the ADC not available, you want to pick up 14 bits. It's mostly available on the market. Another concept you need to know is the full scale value of the DAC. Again, this is something you need to know. We still don't know the internal circuit of the ADC yet, but it doesn't matter because we just know how to use it, right? It's okay. Not everyone can design an ADC, full-scale ADC. So another concept you need to know is the DAC full-scale value. And the reason for that is, if you think about the DAC input, if I'm giving 1111 for the 4-bit DAC we just went through, right? So the R-2R resistor ladder, if we're giving this voltage to it, VL equals what? Can we give a larger number than this to the DAC? It's only 4 bits. What's the maximum number we can give to the input? It's all ones. The superposition, if we turn on all the power supply, it's basically giving all 4 ones to it, right? If we give 4 ones, and this will be the maximum output we can get. We'll see. So remember what are the numbers? 5 over 16 plus
5 over 8 plus 5 over 4 plus 5 over 2.
and this becomes 5 over 16 plus 10 over 16 plus 20 over 16 plus 40?
Yeah.
Yeah. So this is 16 3575. Is that right?
I think so.
You miss 5/16.
What's that?
No, that's right.
This is 516? 15 35 75.
Yeah.
Okay, that's right. Why I know that's right? Very quickly, because wait, this is right? Let me double check here.
Shouldn't it start like at plus 5 instead of plus 2? Plus 5 over 2?
Oh yeah. Wait. Wait. 5 over 16, 5 over 8, 5 over 4. This is right, right?
Yeah.
So 5 over 16, 10 over 16, correct. And this is 4 times 5, which is 20.
20, yeah.
This is 8 times 7, 40. This is right.
Yeah.
Okay. Is this 5 volts?
No. It's like 4.68.
How much difference from 5 volts? I need a one exact answer.
Yeah, it's a 4.6875. So it's
Yeah, a different answer for that.
the difference
How much away from 16 from 5 volts?
would be 0.3125.
Yeah.
Yeah.
Or you can say it's basically, so what is 5 volts? 5 volts is basically 80 over
5/16.
yeah, so this is 5 volts, right? But it's 5 over 16 is less. So it's how much less? It's 1 LSB away from it. Does that make sense? 1 LSB away from it?
Yeah.
Why is making sense?
Because otherwise you wouldn't be able to divide it into any more.
Exactly.
Absolutely.
Yeah, but if you look at this number, you add a 1 LSB, it becomes 1000, right? So that is why it's 1 LSB away from it. And this is whatever analog voltage that is. And this is called the full scale, DAC's full scale voltage, and always being denoted as VFS, the full scale value of the DAC's output. It's VFS. Right? There's an example for you guys. Should I let you do the quiz? We have 7 minutes left. But the quiz is really simple though. We have 8 minutes left. Let's do the quiz. Okay. Let's stop right here and we're going to run more examples on Friday.